Alright, welcome back. As alluded to in the previous video, let's talk a little bit about supercontinents. During the Proterozoic eon, during the Precambrian, um, this is when the supercontinents really kind of first began to form. It wasn't the only eon in which they formed, but this is when we first started getting them. Obviously, we need continents first before we can have supercontinents. Okay, so just in general, a continent is a landmass of crust with much of its surface above sea level, and that crust is granitic crust. When we're talking about continental crust, we're talking it's mostly granite. When we're talking about oceanic crust, it's mostly basalts. So again, a continent is a granitic crust with much of its surface above sea level. But a supercontinent consists of at least two continents merged into one, but for what we've declared it, it's usually all or most of Earth's land masses at a particular time. Some people have heard of the supercontinent Pangaea, which existed at the end of the Paleozoic era, and we'll get to that in Unit 9. So that might be familiar, but there were plenty of supercontinents before Pangaea as well. So as far as plate tectonics is concerned, the present style that we have of plate tectonics doing what they're doing, involving kind of both the opening of ocean basins at divergent boundaries and also the closing of them, convergent boundaries, has almost certainly been established by the Paleo-Proterozoic. So the way our plate tectonics works now, it's how it worked back in the older reaches of the Proterozoic. Remember, before that in the Archean, things were a little faster just because there was a little bit more heat, but by the Proterozoic, we started to lose a lot of that heat, so the plate tectonics, the style of it, very similar to what we see now. Uniformitarianism, folks. Uniformitarianism. In fact, going back to ophiolites, in fact, the oldest known ophiolites providing evidence of ancient convergent boundaries where things are crashing together, where continents are crushing together, actually come from the Neo-Archean, the newest part of the Archean, and the Paleo-Proterozoic, and those rocks can be found in Russia and China. The way supercontinents form is usually one of two ways, usually. All right, you have some landmass, and it splits apart, divergent boundary, creating a new ocean basin. All right, and then for some reason, instead of that boundary being a divergent boundary pushing things away, it switches back, something falls back down, and it turns back into a convergent boundary, and that ocean basin closes. Excuse me. So that's called introversion, where the continents spread apart and then go back into where they came from. Introversion. Extroversion is the opposite of that. So you have some landmass. Right? They break up, new ocean basins created, but instead of kind of like snapping back, they just keep on cruising until they kind of meet on the other side of the Earth or somewhere else on Earth. And that's called extroversion. Imagine them exiting, right? Introversion, they're going back into where they came from. Extroversion, they're exiting and eventually colliding somewhere else. So that's what plate tectonics does. All right, at some point in the future, we will have another supercontinent, maybe in another 100 million years or so, because that's just kind of what happens. Things crash into each other and pull apart, crash into each other, pull apart, crash into each other, pull apart, crash into each other, pull apart. Remember, this is all part of the Wilson cycle. Discussed this in Unit 2, I believe. So initially, the way this all would have started, there would have been just some stable craton. I think they used Africa as an example. Some rifting began, so a divergent boundary, and when the new ocean basin, so the ocean kind of creeps in and keeps kind of pulling apart. But then at some point on the other side of this boundary, perhaps it turned into a convergent boundary, and now this whole thing begins to slide to the right, eventually converging, coming back together, making ophiolites, making a supercontinent. So this is kind of an example possibly of introversion, where it kind of split apart and then came back together. And so this cycle, again, the Wilson cycle is about 205 million years, and this is about-ish how often we're seeing supercontinents formed on Earth. Sometimes it's a little faster than that. Sometimes there's been some about 100 million years between supercontinents breaking apart and coming back together. Sometimes it's a little more than 500 years, but just that's kind of an average. So I think in the past lab, when you were looking at, one of the questions was, what's the very first supercontinent? And it was the supercontinent Earth. So technically, it was the only land mass on Earth, so technically that was all the stuff. So technically that was a supercontinent. But when we think of supercontinents, we're thinking large land masses come together. So the more modern early supercontinents is what we're going to kind of talk about. So again, the early supercontinents may have existed as early as the Neo-Archean, but if so, we don't really have any evidence for them. Remember, a lot of the Archean rocks have been churned up and ate up and subducted or buried, so we don't have a lot of those available to us. But the first supercontinent that geologists recognize in the classical sense of all the land masses coming together was known as Rodinia. And it assembled between 1.3 and 1 billion years ago, and then began fragmenting 750 million years ago. So all the material came together, and then around 1.3 to 1 billion years ago, and then it started to break back up. And it didn't really break back up along the same lines that it came together. So let's look at some images here. So this is 1.15 billion years ago, so kind of right in the middle of that time frame. So here's North America. You can see this is where Arizona is now. Now, when I show you pictures like this, it's kind of misleading, and I'll show you the difference. But just because, the United States, North America is like this now with Arizona down here, doesn't mean that's how it always was. All right. So this could be, and I wish there was like pointing which way north and south was. In fact, in this case, Laurentia, what is kind of North America, part of the U.S., Canada, Greenland, etc., was actually on its side like this. So we should kind of be looking at it from the side. But in any case, so starting around 1.15 billion years ago, so this is all the other stuff starting to kind of crash in, starting to close that ocean basin as things are crashing in. And so notice where Laurentia ends, kind of where the Grenville orogeny was, right, which is actually this stuff down here. And now we're going to fast forward to, and so now this is the beginning of the formation of Rodinia. Now we're going to fast forward to the beginning of the breakup of Rodinia. And when it began to break up, what you can see is the Grenville orogeny is kind of no longer there because it's breaking along these lines. So as things start to break up, what was there is going to now start to go away. What was there is now going to start to go away. So again, this was all part of, again, the North American craton, Laurentia. Here's, my screen went blank. Give me a second here. This is the Grenville orogeny. And as this is coming together, that finally gets smushed on there. But this whole part, once it breaks up, is going to break off and go away this way. All right. So you can see that in this. So this is kind of pre-Rodinia, what we had for Laurentia. And this is kind of post-Rodinia. You can see that the big chunk of this is gone. That chunk, after Rodinia came together, the piece that kind of moved off away this way took a big chunk of the Grenville province with it, and part of the granite rhyolite province as well. So again, how they come together is not always how they separate apart. That's like saying, if I put my hands together, and then when I took them apart, they took these two fingers with it. All right, they took those two fingers with it. So it's not like they come together and go apart perfectly. Sometimes they've done that, but sometimes they'll come together, suture together, and take part of one continent with it as it travels away. So here's actually the possible configuration of the Neo-Proterozoic supercontinent Rodinia, but right before it began breaking up around 750 million years ago. So here's Laurentia, and this is actually North America on its side. So these are the Great Lakes. This is Canada here. This would be what's left of the U.S. Here's Arizona would be here, so we're turned this way. We're turned on its side. And look, we're also right along the equator at this point. So again, sometimes those pictures don't quite give us justice. And as this is breaking up, what was the Grenville orogeny kind of got taken with it to Africa. Go figure. So we can match up rock samples from North America and Africa and see at one point those two things were together. Again, this is all based on evidence, paleomagnetism evidence as well. That's how we know exactly what, which way everything was tilted. The strength of it, we can also tell where it was in relation to the equator. So yeah. So this isn't just a guess. This is, evidence, information. The rocks kind of tell us where, what things were connected. Paleomagnetism tells us the orientation and where on Earth it was, how far north or south it was as well. So after Rodinia, after the separation of Rodinia, the next supercontinent that formed on Earth was Pannotia, starting about 650 million years ago. So after the breakup of Rodinia and the formation of Pannotia, it only took about 100 million years or so. The word Pannotia, and this is kind of important, comes from two Greek words, pan meaning all, and notos meaning south. So Pannotia means all southern land. And the reason that's important is because all of Earth's crust, when they combined to form a supercontinent, were on the South Pole, or on the bottom of the Earth. So it lasted for about 100 million years and started breaking up around 550 million years ago. And that kind of helped to mark the beginning of the Phanerozoic Eon, which started 542 million years ago. So here's a kind of an interesting image if we kind of expanded all of Earth. Yeah, so all southern land. So everything kind of met kind of at the South Pole. So here's maybe a little bit better view. If I was looking down at Earth on the North Pole, nothing here. If I was looking at the South Pole, there's all the stuff. Everything kind of collected down there. Now, does that mean that it was cold? Well, not necessarily. Where continents are dictates ocean currents. Ocean currents help to dictate weather. So if the continents are in a different place, then the ocean currents are in a different place, then therefore the climate is doing something different. So there could have very well been ice, and we'll get into glaciation here in a little bit. In fact, there was evidence, but this is just kind of showing you kind of how everything was put together. But it might not necessarily be what we think about today, being, oh, well, Antarctica is at the South Pole and it's just a big chunk of rock covered in ice. That might not necessarily be the case. Different atmosphere, which we'll get into later in this unit, different climate. I mean, it all plays a part, right? The geospheres connect to the atmosphere, which connected to the hydrosphere, etc., etc. So don't think Antarctica necessarily. There could have been some glaciation. It may have been less, may have been more than what we had today, what we see today or think of today when we think of Antarctica at the South Pole. But in any case, we'll get to glaciation in a later section. And in fact, there it is right there. So let's pause here. When we come back, let's talk about some glaciation during the Proterozoic. See you back here in just a second.